A production alert fires at 2:47 a.m. The on-call engineer pulls up the payment reconciliation module, a feature the team shipped just 3 weeks ago in record time, 2 days flat, powered by GitHub Copilot. The code is syntactically clean. It passes all tests. But as the engineer scrolls through the AI-generated logic, a cold realization sets in. Nobody on the team, not the author, not the reviewer, not the architect, can answer a single question: why does this conditional branch exist? What business rule does it encode? The developer who accepted the Copilot suggestion remembers approving it, because it looked right. But looking right and meaning something specific are not the same thing. That gap between code that compiles and code whose intent is understood is now costing this team hours of production downtime. And here is what makes this different from every other debugging story you have heard before. The intent was never lost. It was never encoded in the first place. By the end of this lecture, you will have the vocabulary, the diagnostic framework, and the prescriptive workflow to ensure this never happens to your team again. Now, your first instinct might be to reach for a familiar label. This is just technical debt, you say. Or perhaps they simply lack documentation discipline. But both diagnoses are wrong, and understanding why they are wrong is the entire foundation of this lecture. Technical debt, as Ward Cunningham originally defined it in 1992, describes the cost of rework accumulated when you choose a faster, simpler solution today over a better architected one. The debt is in the structure. You can refactor your way out of it. Poor documentation is a communication failure. You had the knowledge, you failed to write it down. You can recover it by interviewing the original engineers. But intent debt is categorically different. There is no original knowledge to recover. The developer who accepted the AI suggestion did not make a deliberate choice between two known approaches. They accepted a statistically plausible token sequence generated by a language model. The why, the business rule, the edge case rationale, the architectural constraint was never in any human mind connected to that code. This is not a debt you can refactor away. It is a void, and voids require a completely different remediation strategy. But here is the uncomfortable question. How much of your current codebase is already filled with these voids? So where does this concept formally come from? In early 2026, Martin Fowler, whose 2003 work on technical taxonomy remains foundational reading for any systems architect, published a fragments post titled Intent Debt in the LLM Coding Era. It was not a long piece. Fowler rarely needs length to land a point. But the developer community treated it as a signal moment. Within 48 hours, the post surfaced on Geek News, the Korean developer community's equivalent of Hacker News, and generated one of the highest engagement threads of that quarter. The reason the community responded so viscerally is precisely because Fowler gave name to something engineers had been experiencing for over a year without the vocabulary to articulate it. A problem without a name cannot be systematically solved. You cannot write a post-mortem category for it. You cannot build a checklist against it. You cannot train junior engineers to avoid it. The naming of intent debt is not a semantic exercise. It is the prerequisite for every mitigation strategy that follows. And in the next section, I will show you exactly what those strategies look like, and what capabilities you will walk away with after this lecture. Let me be precise about what this lecture delivers, because precision about learning outcomes is itself a form of intent preservation. By the time you finish all 6 chapters, you will have 4 concrete, deployable capabilities. First, you will be able to diagnose intent debt in an existing codebase, not intuitively, but using a structured assessment protocol with measurable indicators. Second, you will be able to classify intent debt severity across 3 levels, latent, active, and critical, which maps directly to prioritization decisions in your technical roadmap. Third, you will be able to apply the 4 intent preservation principles to any AI-assisted coding workflow, whether you are using Copilot, Cursor, Claude, or any successor tool that ships in the next 18 months. And fourth, and this is the one most team leads tell me is the most operationally valuable, you will be able to restructure your team's AI coding workflow so that intent is captured at the moment of generation, not tempted as a retrofit 3 weeks later when a production fires at 2:47 a.m. 4 capabilities, systematic, applicable from day one. But which teams is this actually built for? That is the question I want to answer precisely next. This lecture is not for everyone, and I mean that as a design principle, not a limitation. It is built for 3 specific roles: team leads and engineering managers who have already rolled out AI coding tools to their teams and are beginning to feel an uncomfortable intuition that something is being lost in the velocity gains, even if they cannot yet name what that something is. Software architects and principal engineers who are responsible for codebase longevity and who understand that a system which cannot be reasoned about is system 1 incident away from catastrophic failure. And senior engineers 5 or more years of experience, who have enough pattern recognition to sense that the code emerging from AI-assisted workflows feels different in a qualitative way they cannot yet articulate to their managers. If you are newer to the field, this lecture will still be valuable, but its prescriptions assume you have already felt the comprehension strain firsthand. Because intent debt, like most systemic risks, is invisible until you have enough context to recognize what healthy comprehension actually looks like. The next chapter will give all three of these roles a precise, shared definition to work from. Because before we can solve intent debt, we need to agree on exactly what we are solving. Welcome to the lecture. The crisis has a name now. Let us build the framework to defeat it. To understand intent debt, we must first go back to where debt thinking began. In 1992, Ward Cunningham, one of the original signatories of the Agile Manifesto, introduced a now famous metaphor while presenting at OPSLA. He described the act of shipping immature code as borrowing money. You get speed today, but you pay interest tomorrow in the form of extra effort required to work around that immature code. This was a revolutionary framing. For the first time, engineering shortcuts had a financial language that the business stakeholders could grasp. The metaphor was deliberate and precise. Cunningham was specifically describing a conscious trade-off, a calculated risk taken with full awareness. The team knew the debt existed. They chose to incur it. And crucially, they intended to repay it. That word, intent, is the seed of everything we're building toward in this lecture. But as we'll see, the moment AI enters the picture, that seed gets buried where no one can find it. Martin Fowler refined Cunningham's original metaphor into something far more precise in 2003. His technical debt quadrant maps debt along two axes. First, whether the debt was deliberate or inadvertent. Did you know you were cutting corners? Second, whether it was reckless or prudent. Was the trade-off thoughtful or careless? This gives us 4 categories. Deliberate and prudent. We know this is a shortcut, we'll fix it after launch. Deliberate and reckless. We don't have time for good design. Inadvertent and prudent. Now we know the better approach. Inadvertent and reckless. What's layering? Every single cell in this quadrant shares one invisible assumption. A human being made a decision. A person with context, with knowledge of the business domain, with awareness of constraints, sat down and either chose or failed to choose an approach. That assumption is so deeply embedded we never even thought to question it. Until now. Because what happens when the entity generating code has no context, no domain knowledge, and no awareness of constraints whatsoever? Here is the breakpoint. Precise moment where 30 years of technical debt theory stops applying. Fowler's quadrant, Cunningham's metaphor, every debt framework in the NIST software assurance literature, all of them carry an invisible axiom. Behind every line of code, there was a human who decided to write it that way. Even the worst reckless inadvertent debt still has a person behind it. Someone who could, in theory, be interviewed. Someone whose reasoning could be reconstructed. But when a developer types a prompt into an AI coding assistant and accepts the generated output, the entity that wrote the code, the model, has no intent. It has pattern completion. It has token probability. It does not have goals, constraints, or trade-offs. The code may be syntactically correct, even architecturally sound by some metric. But the why, the reason that specific structure was chosen over alternatives, the constraint that made this the right approach, that reasoning simply never existed. The quadrant has a blind spot the size of every AI-generated codebase on the planet. And that blind spot has a name. We'll define it precisely right now. Before we arrive at intent debt, we need to cross a bridge concept that most teams already sense, but haven't formally named. Cognitive debt. Cognitive debt is the accumulated cost that teams pay when code cannot be reasoned about without significant mental reconstruction effort. Notice carefully, this is distinct from technical debt. A system be architecturally clean, well-tested, even beautifully structured, and still carry enormous cognitive debt if the mental model required to work with it is expensive to build and maintain. John Sweller's cognitive load theory from educational psychology gives us the right vocabulary here. Every developer working on a codebase holds a working memory model, a live map of what the code is doing and why. When that model is expensive to construct, expensive to hold, and collapses the moment the developer steps away, you have cognitive debt. The interest on cognitive debt is paid in onboarding time, in bug investigation hours, in the paralysis developers feel before touching unfamiliar modules. And here's what makes it dangerous. Cognitive debt is invisible on every dashboard your organization currently uses to measure software health. But if cognitive debt already existed before AI, why are we escalating to a new term entirely? Let's make this concrete with a comparison. In a pre-AI team, cognitive debt accumulates gradually. A developer writes a module over 2 weeks, makes decisions under pressure, and leaves without adequate comments. Another developer joins 3 months later and spends 2 days reconstructing the original developer's mental model. Painful, There's a Git history, there are PR comments, there might even be a Slack thread. The cognitive debt is real, but it's bounded. Now consider an AI-assisted team running at scale. A senior architect writes a 2-line prompt. The AI generates 400 lines of code in 8 seconds. The architect reviews, it looks reasonable, it passes tests. Accepted. 6 months later, a junior developer needs to modify that module. There is no Git archaeology that reveals intent. There is no PR discussion. There is no why trail at all. The AI had no reasoning to leave behind. What used to take 2 weeks to accumulate in cognitive debt, the gradual erosion of context, now happens in 8 seconds. AI doesn't just create cognitive debt faster. It fundamentally changes the debt's character, because as there was never a human mental model to reconstruct in the first place. That distinction is exactly what defines the third and most dangerous layer, intent debt. We now have everything we need to define intent debt with precision. Intent debt is the gap between what code does and why it does it. Specifically, the loss of the reasoning, constraints, and trade-offs that motivated a design decision, when that reasoning was never captured, communicated, or made recoverable. Let me be exact about each word in that definition. What code does is the functional domain, behavior, outputs, interfaces. This is what tests verify, what linters check, what AI tools excel at producing. Why it does it is the intentional domain, the business constraint that ruled out alternative B, the performance requirement that forced this architectural pattern, the security threat model that made this approach non-negotiable. These are not comments. These are not README files. These are the living, contextual, decision-making structures that allow a team to safely evolve a system over time. When a developer asks, "Can I refactor this module?" the answer requires access to the why. If the why never existed, as is the case with AI-generated code accepted without explicit intent documentation, the answer is unknowable. Not unknown, unknowable. That is intent debt, and it is a categorically different problem from anything the classical debt frameworks were designed to address. Now let's see the full arc of how we arrived here. The evolution follows a clear 3-stage progression, and each stage is amplified by AI tooling in a distinct way. Stage 1. Technical debt. The problem is structural, bad code that needs cleanup. The solution space is well understood: refactoring, code reviews, automated quality gates. AI accelerates this stage by generating more code faster, increasing the volume of structural debt. Stage 2. Cognitive debt. The problem is comprehension, code that cannot be reasoned about. The solution space is partially understood: documentation, knowledge transfer sessions, architectural decision records. AI accelerates this stage catastrophically by removing the human reasoning trail that made recovery possible. Stage 3. Intent debt. The problem is existential: design decisions whose rationale never existed in any recoverable form. Solution space is not yet standardized. This is the frontier. And critically, intent debt is not a subset of cognitive debt, just as cognitive debt is not a subset of technical debt. Each stage contains the previous, but introduces a qualitatively new failure mode. You can resolve all your technical debt and all your cognitive debt and still be drowning in intent debt. This 3-stage model is the analytical frame that everything in this lecture is built on. So how do you know if your organization is accumulating intent debt right now? There are 5 observable symptoms. And if your team has been using AI coding assistants for more than 3 months, I would be surprised if you don't recognize at least 3 of them. First, nobody on your team can justify the major architectural choices in AI-generated modules without saying the AI suggested it. Refactoring proposals stall in review, not because the new approach is wrong, but because no one can confirm the original approach's constraints are no longer valid. Third, onboarding time for new developers has spiked even as code volume has increased, a paradox that only makes sense if the comprehension cost per line has risen. Fourth, test coverage breaks in unexpected ways after AI-generated changes, and the team cannot explain which business rule was violated or why the test existed in the first place. And fifth, the one that should concern every engineering leader in this room, your bus factor is approaching 1. Not because only one person wrote the code, but because only one person, the one who wrote the prompt, had any memory of why it exists. And even their memory is a prompt, not a decision. In the next chapter, we will build a complete taxonomy of intent debt, classifying it precisely so that we can finally measure what we've been unable to name. Let's dissect exactly where intent disappears. Intent debt does not strike uniformly. It operates in 3 distinct layers, each more dangerous than the last. The first and most devastating is architectural intent debt. This is the macro layer, the system-level decisions that shape everything below them. When AI generates a service boundary, a data partitioning strategy, or a retry policy, it produces a structurally plausible output, but it never records the trade-off reasoning behind it. Why was this a microservice rather than a module? Why was eventual consistency accepted here? In traditional architecture practice, we capture these decisions in architecture decision records, ADRs. But when AI drives the scaffolding, no human deliberation occurs, so no ADR gets written. The system exists. The rationale does not. 6 months later, a new engineer asks why the event bus was chosen over direct RP, and there is simply no answer in the codebase. That silence is architectural intent debt at its most dangerous. But this is only the top layer, and the layers beneath it are where your daily work quietly breaks down. The second layer is design intent debt, and this is where your architects and senior engineers feel the daily friction. At the module and class level, AI tools like Copilot and Claude Code are extraordinarily good at suggesting clean-looking separations of responsibility. A user service here, an account manager there, a notification coordinator somewhere else. The boundaries look reasonable. The naming is professional. But here is the critical question. Was that boundary drawn because of a domain model insight, a bounded context from domain-driven design, or a performance isolation requirement? Or was it drawn because the AI's training distribution suggested it looked right? When a human architect draws a module boundary, there is a mental model behind it, often connected to Conway's law, to team ownership, or to anticipated change vectors. When AI's the same boundary, that mental model is absent. It was never formed. The boundary exists, but the reasoning for it is structurally invisible. This means that when requirements change, and they always change, the team cannot evaluate whether the existing boundary should flex or break. They are navigating a map drawn by someone who never walked the terrain. And at the smallest scale, something even more insidious is waiting. The third layer is implementation intent debt, and while it operates at the smallest scale, it is often the source of the most time-consuming incidents. At the code block level, we are talking about algorithm choices, specific constant values, and edge case handling that have no accompanying explanation. Consider a retry loop with a hard-coded backoff of 2.7 seconds, or a algorithm that switches strategy at a threshold of 512 elements, or a null check placed before a specific operation but not before another. When a human engineer writes this code, they typically know why. A production incident drove that backoff value, a benchmark justified that threshold, a race condition motivated that null guard. When AI generates equivalent code, it produces these specifics based on statistical pattern matching. The values look reasonable. The logic compiles and passes tests, but the provenance, the why, is gone from the moment of creation. There was never a human who knew the reason to document it. This is what I call micro-intent loss, and it is especially treacherous because the code works until the underlying assumption changes, and then it fails with no diagnostic trail. Now that we understand the 3 layers, the next question is critical. How do we measure and prioritize which of these debts to address first? Understanding the 3 layers gives us the vocabulary. Now we need a triage framework, because not all intent debt is equally dangerous, and teams with limited capacity must know where to act first. I want to introduce a 2-axis severity classification matrix that I have applied across multiple enterprise engagements. The first axis is scope. Does this missing intent affect a single local function, an entire module, or the full system architecture? The second axis is recoverability. Can the intent be reconstructed through code inspection alone? Does it require finding the original author, or is it permanently and irrecoverably lost? Crossing these 2 axes produces 6 severity cells. At the lowest end, a local function with recoverable intent. A competent engineer can reconstruct it in minutes through inspection. At the highest end, system-level intent that is permanently lost. This is the cell that triggers architectural rewrites and costly migration projects. The critical insight here is that recoverability degrades over time. Intent that is author-dependent today becomes permanently lost the moment that engineer leaves the team or the context fades. This matrix is not just a classification tool, it is a time-sensitive warning system, and the question of which cells to prioritize brings us to something the matrix alone cannot tell you. The severity matrix tells you how bad a debt is in isolation. But the most dangerous intent debt is not simply the most severe. It is the most severe debt sitting on the most frequently changed code. This is the concept of debt hotspots. Think of it as a risk intersection. Severity classification on one dimension, code change frequency on the other. SFV6 catastrophic intent gap in a legacy module that nobody has touched in 3 years is a problem, but it is a stable problem. The same SEV6 gap in a high-churn critical path module, one that your team modifies in every sprint, is an active organizational hazard. Every change made without understanding the original architectural constraints is a change that could silently violate them. I have seen this pattern produce cascading failures in payment processing systems where a high-frequency settlement module was repeatedly modified by engineers who had no access to the original capacity planning rationale. The module worked until it didn't, at a scale the original constraints had warned against, in documentation that was never written. The practical prescription is this: rank your intent debt remediation backlog by multiplying severity score by change frequency. That intersection, unrecoverable system-level intent in high-churn critical path code, is where you must act first, and act urgently. In the next session, we will trace exactly how AI tools mechanically produce each of these debt types. And the answer is more structural than you might expect. Now we arrive at the mechanism, the specific workflow patterns in AI coding tools that mechanically produce each type of intent debt. This is not a criticism of the tools themselves. It is a structural analysis of how their interaction models were designed and what those designs systematically omit. Consider the standard Copilot workflow. A developer types a function signature or a comment. Copilot generates a completion. The developer reviews it, typically in under 4 seconds, research shows, and presses tab to accept. In that 4-second window, the developer is evaluating plausibility. Does this look right? Does it compile? Does it follow the naming convention? What they are almost never evaluating is rationale. Why this algorithm? Why this boundary condition? Why this abstraction level? The tool was not designed to ask that question, and the interaction model provides no natural moment to record the answer. With Claude Code and similar agentic systems, the pattern is amplified. You prompt for a feature, receive a multi-file implementation, review the diff, and merge. The entire prompt response cycle is conducted in a conversational interface that feels like a decision was made. But decisions without recorded reasoning are indistinguishable from accidents when you revisit them later. This is what I call autocomplete as Oracle syndrome. The fluency and confidence of AI output suppresses the developer's instinct to question and document. The tool looks certain, so certainty feels achieved. The workflow problem is actually the smaller issue. The structural limitation underneath it is far more fundamental. The workflow problem is behavioral. It can theoretically be addressed with discipline and process. But the second mechanism is structural, and it is baked into the fundamental architecture of every large language model in production today. Every AI coding assistant operates within a context window, a finite amount of text the model can attend to in a single session. Current flagship models range from roughly 100,000 to 200,000 tokens. That sounds large, but a real enterprise codebase can span millions of lines across thousands of files, representing years of accumulated architectural decisions. The AI operates on a slice. It cannot see the whole. More critically, every new session begins with zero memory of previous sessions. The constraint you established with Claude on Monday, that this service must never exceed a 50 milliseconds E99 latency, because it sits on a synchronous, user-facing critical path, is completely invisible to Claude on Thursday when you ask it to add a new feature. This is session amnesia, and it means that AI-generated code from session to session is not architecturally coherent by default. Each session is a fresh context with no access to the constraint propagation that human architects carry in their heads across months of work. The result is what I call structurally incoherent intent. That looks internally consistent in any local view, but violates its own architectural principles across the full scope. And this is precisely why Chapter 4's 4 principles of intent preservation are not op process improvements. They are existential necessities for any team building production systems with AI assistance. In the previous chapter, we dissected intent debt into 4 taxonomic layers: structural, behavioral, constraint, and decision debt. Now the critical question is, how do we stop accumulating it? The first principle is deceptively simple, yet almost universally violated. The prompt that generated your code is not a throwaway input. It is a design record. Think about this carefully. Every architecture decision record, every design document, every RFC your team has ever written, its purpose is to answer the question, why does this code look the way it does? In the AI era, the single richest source of that answer is the prompt. When you discard it, you are destroying a primary source document the moment it is created. From this point forward, treat every intent-bearing prompt exactly a commit message or an ADR. It must be versioned, it must be reviewed, and it must live alongside the code it produced. This is principle 1. Prompt as artifact. But just saying save your prompts is not enough. The real insight is in how you structure them to carry maximum intent signal, and that is what we will build right now. Let me show you what this looks like in practice with a concrete before and after that will make the problem viscerally obvious. A developer working on a payment retry system writes this prompt. Write a retry function for failed payments. The AI generates code. The code works. It gets committed. 6 months later, a new developer asks, why does this retry 3 times? Why exponential backoff and not linear? Why does it stop retrying on HTTP 422, but not 429? None of those answers exist anywhere in the codebase. That is intent debt crystallized. Now watch the same prompt rebuilt with the prompt to ADR workflow. The prompt opens with context. We are building a payment retry handler for a PCI DSS compliant system where the upstream processor charges per retry attempt above 5 attempts per minute. It then states constraints. Maximum 3 retries, exponential backoff to avoid processor rate limits. Hard stop on validation errors 422 because retrying those wastes money. Keep retrying on 49 because those are transient throttles. That single structured prompts directly to an ADR entry. The AI's output is now anchored to documented reasoning. The before prompt produces working code with 0 intent. The after prompt produces working code plus a comprehension trail that survives team turnover. The difference is not the code, it is the intent that travels with it. And Principle 1 only works if it is enforced, and enforcement without tooling is just a policy document nobody reads. Here is how you make prompt as artifact act non-optional. First, you commit prompt metadata as a sidecar file. When a developer generates code using any AI tool, a companion file, call it the .prompt file, is committed alongside the source file. It contains the raw prompt, the AI model, the timestamp, and a free text rationale field. Second, you add a lightweight CI linting step. The linter inspects every pull request and flags any changed source file that lacks a corresponding .prompt sidecar or inline prompt annotation. It does not block builds for minor style changes, but it blocks merge for any structural addition or algorithm change with no prompt record. Think of it exactly like a missing unit test. Your CI pipeline already knows how to express that social contract. The third layer is the git commit hook that validates prompt metadata completeness before allowing the commit to proceed. Look at this sample pre-commit configuration on screen. 3 lines of shell script that check for the presence of a prompt annotation in modified files. This is not bureaucracy. This is the same muscle memory your team already has for linting and test coverage. The question is not whether you can afford to do this. The question is whether you can afford what happens to your codebase in 18 months if you do not. In the next principle, we go deeper. Because saving prompts solves only half the problem. Here is a failure pattern that every experienced architect has now seen at least once with AI coding tools. A developer opens a fresh AI session, describes a feature, gets back code, ships, and 3 weeks later a security review finds that the generated implementation bypasses the team's established rate-limiting layer entirely. Not because the AI was malicious, not because the developer was careless, but because nobody told the AI that a rate-limiting layer existed. The AI had no context. It solved the stated problem optimally within the information it had. And the information it had was incomplete. This is the core failure that Principle 2 addresses. An AI model without declared constraints is not just operating in a vacuum. It is actively dangerous because it will produce coherent, well-structured, confidently written code that violates constraints it was never told about. The solution is a mandatory discipline. Every AI coding session must open with explicit constraint declaration before any feature is requested. Not occasionally. Not for complex features. Every session. The constraint declaration functions exactly like the preamble in a legal contract. It establishes the universe of rules within which everything that follows must operate. Performance bounds, security requirements, domain invariants, team conventions, and critically, approaches that have already been tried and rejected. When you prime an AI with this context, you are not limiting its creativity, you are directing it toward a solution space that is actually deployable in your system. Now let me show you what this looks like as a reusable team artifact. What you see on screen now is a reusable constraint declaration template. We call it the project context file, or PCF. This is not a novel idea. It maps closely to the system prompt concept in an AI API design, but operationalized for engineering teams rather than product teams. The PCF lives in your repository root. It is version controlled, and every developer is expected to paste it or reference it via your AI tool's context injection feature at the start of every significant AI session. Walk through the sections with me. The first block declares architectural constraints, your service communication pattern, your database access rules, your caching strategy. These are the load-bearing walls of your system. The second block captures team conventions, naming patterns, error handling idioms, the logging framework you standardized on. The third block, and this is the one most teams skip, is the rejected approaches registry. This is where you document that you tried GraphQL for this service and abandoned it, that you evaluated Redis cluster and chose a simpler solution, that event sourcing was prototyped and deemed too complex for the current team size. The fourth block covers known domain edge cases. the business rules that only become visible after a production incident, the data anomalies that exist in legacy records, the time zone handling quirks specific to your customer base. A PCF that is maintained and actually used will eliminate perhaps 60% of the constraint violation patterns we classified as intent debt in the previous chapter. But maintaining it requires the discipline of Principle 3, which introduces a human gate that the AI cannot replace. Code review is the most expensive quality gate in software engineering, and in most organizations, it is now systematically broken for AI-generated code. Not because reviewers are lazy, but because the review model was designed for a different era. Traditional code review asks 3 questions. Does this code work correctly? Is it clean and readable? And does it follow our style standards? Those are necessary questions, but they are entirely insufficient for AI-generated code. And here is the precise reason why. AI-generated code is typically cleaner, better formatted, and more syntactically consistent than human-written code. It passes traditional review criteria easily, and that is exactly what makes it dangerous. A reviewer approves a beautifully written caching implementation without ever knowing that the AI chose LRU eviction because it is the textbook default when your domain's access pattern is actually scan-heavy and requires you. The code works, the tests pass, the review passes, and a subtle performance assumption is now encoded in your production system with 0 documented rationale. Intent review is the new gate that closes this blind spot. It does not replace code review, it adds a second lens that asks a different set of questions. Where traditional review verifies correctness, intent review verifies comprehension. The reviewer must be able to answer why questions, not just what questions. If the reviewer cannot explain the reasoning behind a structural or algorithmic choice in an AI-assisted PR, that PR does not merge, regardless of how clean the code looks. The contrast is stark, and the implementation checklist makes it concrete. Here is the intent review checklist. 5 questions that every reviewer must be able to answer before approving any AI-assisted pull request. Print this. Put it in your PR template. Make it a required section in your GitHub or GitLab merge request form. Question 1. Can you explain why this particular structure or architecture was chosen? Not what it does, but why this approach over alternatives. If the reviewer cannot answer this from reading the PR alone, the PR is missing its rationale documentation. Question 2. What algorithm or design pattern did the AI select, and have you verified it is appropriate for this domain's actual usage patterns? Not just textbook defaults. Question 3. What approaches were considered and rejected during generation, and is that rejection reasoning recorded? This directly maps to the rejected approaches registry in your PCF. Question 4. Which constraints from the project context file drove this implementation, and can you point to where each constraint is honored in the code? Question 5. Who on the team owns the domain knowledge to confirm this is correct, and have they been tagged as a reviewer? This last question is the comprehension test. It forces the PR author to identify the human who holds the contextual knowledge that the AI did not have. Together, these 5 questions take approximately 5 additional minutes per PR. The cost of skipping them is what we documented in the anatomy of intent debt. The teams that internalize this discipline stop accumulating structural debt from AI tools. And in the next chapter, you will see exactly what that looks like, production codebases that got it right. The first 3 principles protect intent at the moment of creation, at prompt time, at generation time, at review time. But codebases are living systems. They accumulate months and years of changes, and even a perfectly dotted module from 6 months ago can become an intent orphan, a body of code whose documented purpose has drifted away from its current reality. Principle 4 addresses this temporal dimension. A living intent map is a lightweight, continuously maintained document that provides a comprehension layer over your entire codebase. It is not API documentation, it is not a README, and it is not a wiki page that nobody updates. It is specifically structured around 4 data points per module. The original purpose and the problem it was created to solve, the key constraints that must remain honored, the alternatives that were explicitly rejected during design, and the current human owner of that intent. Meaning the person who can be paged at 2 a.m. and explain why this module exists. Think of it as a module-level ADR index combined with an intent ownership registry. The map structure you see on screen covers the major dimensions. From the center outward, purpose, constraints, rejected, alternatives, and intent owner. Each module in your codebase gets a card. The card is small. Maintaining it takes minutes per module per quarter. But the absence of this map is precisely what makes large AI-assisted codebases feel like archaeology projects rather than engineering systems. Here is the uncomfortable question. Does your team currently have any systematic way to answer? For any module, why it looks the way it does today? If the answer is no, you already have intent debt. And it is compounding. A living intent map that nobody updates is worse than no map at all, because it creates false confidence. The operationalization of Principle 4 requires two automated mechanisms. The first is staleness detection. Your tooling monitors the diff volume between a module's last code change and the last update to its intent map card. When the code diverges beyond a configurable threshold, say more than 30% of lines changed since the last intent card update, the system flags that module as intent stale and blocks AI-assisted changes to it until the intent card is reviewed. This is a direct parallel to test coverage enforcement. You already know how to express this social contract in CI. The second mechanism generates an intent coverage metric for your codebase. This is a single percentage. What fraction of your modules have a current, non-stale intent map card? This metric belongs on your engineering health dashboard alongside test coverage and security vulnerability counts. It makes intent debt visible as a first-class measurement, not a vague feeling. A codebase at 90% intent coverage feels radically different to work in than one at 20%. New developers onboard faster. AI sessions produce better aligned output because the PCF can be populated from the maps. And incident response is faster because you can trace why does this module behave this way in minutes rather than hours. These four principles, prompt as artifact, constraint first prompting, rationale review as gate, and living intent maps, form a complete system. In the next chapter, we move from framework to evidence. Real teams, real code bases, and the measurable outcomes that prove this system works at scale. Let me show you a pattern I have seen repeated across large enterprises, and it is not a success story, at least not at first. A financial services firm with 150 engineers rolled out Git Copilot across 3 development teams in Q1. Within 60 days, velocity metrics were up 34%. Leadership declared victory. But here is what the dashboards did not show. Intent debt was accumulating silently in every module those engineers touched. By month 4, the team hit what I call the comprehension crisis, a point where a critical payment routing service required architectural regression, because no one, not even the original authors, could confidently explain why specific validation constraints existed. The AI had generated the code. The code worked. But the reasoning had evaporated. This 3-phase pattern, productivity spike, silent accumulation, then crisis, is now the canonical enterprise AI adoption arc. And the teams that got this right were the ones who recognized phase 2 before it became phase 3. The question is, what were the early warning signals they learned to read? We will look at the exact diagnostic instruments they used right after this. Before this team could fix anything, they had to measure what they were actually dealing with. And this is where most remediation efforts fail. Teams to solutions without establishing a baseline of how severe the intent debt actually is. This team deployed 3 diagnostic instruments in parallel. First, a comprehension survey. Every engineer on a module was asked to explain in plain language why a specific block of logic existed. Not what it did, but why. The results were alarming. On AI-generated modules, fewer than 30% of respondents could provide a rationale that matched the original intent. On human-authored modules, that number was 71%. Second, a bus factor audit per module, not for the codebase as a whole, but granular, module by module. They found that 12 of their 47 path modules had a bus factor of exactly 1 person. Third, they measured time to explain. How many minutes did it take an experienced engineer articulate the design rationale for a critical function to a new team member? On AI-generated code without intent markers, the average was 23 minutes. With structured intent documentation, 4 minutes. That is a 5x comprehension penalty. These 3 instruments together gave them a severity map, and that map determined where they would strike first in remediation. But the remediation strategy itself had its own structure. Let me show you exactly how they executed it. With the severity map in hand, the team designed what they called an intent recovery sprint, a structured, time-boxed remediation cycle that targeted the highest severity, highest churn modules first. The sequencing logic was deliberate. High severity plus high churn means these modules are both the most dangerous and the most likely to accumulate new intent debt even while you are fixing old debt. So you must apply the 4 principles as a shield during recovery, not after. The sprint ran in 4 phases. Phase 1, triage, where the severity map was converted into a ranked module backlog. Phase 2, constraint injection, where each critical module received explicit decision records embedded directly in the code, not in a separate wiki, but co-located with the logic. Phase 3, validation, where the comprehension survey was re-administered to the same engineers after injection to verify recovery. And Phase 4, guardrail installation. The team configured their pipeline to flag any new AI-generated commit that lacked a co-located intent marker, making accumulation structurally harder going forward. The result after one 4-week sprint Comprehension accuracy on treated modules rose from 28 to 67%. Not perfect, but the trajectory was reversed. What is remarkable here is not just the outcome. It is that the 4 principles you learned in Chapter 4 became operational constraints, not aspirational guidelines. The next question is, where exactly does this fit in your existing architectural toolchain? That answer is more elegant than you might expect. One of the most common objections I hear from architects is we already have ADRs. We already use the C4 model. We already do documentation as code. Do we really need another layer? This is precisely the right question. And the answer is, intent debt management is not a new layer. It is the connective tissue that was always missing between your existing layers. Let me map this. Architecture decision records, ADRs, capture why architectural decisions were made at the system level. The C4 model documents what the system looks like at 4 levels of abstraction: context, container, component, code. Documentation as code tools like Backstage or Docusaurus keep technical docs versioned alongside source. But here is the gap. None of these tools operate at the function-level reasoning layer, the layer where AI code generation actually operates. When Copilot writes a validation function, it is not making an ADR-level architectural decision. It is making a micro-decision at the code logic layer. And that is exactly where living intent maps plug in, sitting between your component-level C4 documentation and your actual code, capturing the reasoning at the granularity where AI generation happens. This is not a replacement for your existing tool chain. It is the missing rung on the ladder. And once engineers see this positioning, resistance drops dramatically, because it frames intent debt management as completing an existing investment, not competing with it. But toolchain fit alone does not determine success. What actually separates teams that get this right from teams that do not? The answer will challenge your assumptions about process versus culture. Here is the finding that consistently surprises engineering leaders. The single strongest predictor of success in AI coding governance is not the toolchain chosen. It is whether the team treated it as a process addition or as a cultural and toolchain transformation simultaneously. Let me show you the divergence in concrete terms across a 12-month adoption window. Teams in the process addition camp added intent documentation requirements to their definition of done, ran training sessions, maybe configured a linter rule. At month 3, compliance was around 60%. By month 6, it had drifted to 40% under delivery pressure. By month 12, the practice had been quietly abandoned and intent debt was accumulating faster than before the intervention, because engineers now had even more AI tooling and zero structural constraints. Contrast this with transformation teams. They did something different in the first 30 days. They rewired the incentive structure. Code review was modified so that a pull request with AI-generated logic but no co-located intent marker could not be approved. Not should not, could not. Intent documentation became load-bearing, not ornamental. The toolchain enforced what the culture promoted. At month 12, comprehension scores on AI-generated modules in these teams were statistically indistinguishable from human-authored modules. The lesson here is architectural in its own right. Constraints that live in culture eventually yield to pressure. Constraints that live in toolchain are structural. The most effective teams made intent preservation both. And this insight leads us directly into how this connects to the broader landscape of concepts you may already be working with. Because intent debt does not exist in isolation. Intent debt does not exist in a vacuum. To position it precisely for your organization, and to avoid the trap of reinventing solutions that already exist, you need to understand exactly which problems it shares with adjacent concepts, and crucially, where it diverges. Consider software entropy, the general tendency of a codebase to degrade in structure and coherence over time. Intent debt contributes to entropy, but entropy can exist even in perfectly human-authored codebases. Intent debt is specifically a cognitive phenomenon. It is entropy of understanding, not just entropy of structure. Knowledge management debt is closer. It describes the accumulated cost of failing to externalize organizational knowledge. Intent debt is a subset, but more targeted. It lives specifically at the code logic layer, not at the process or domain knowledge layer. Documentation debt is the most commonly confused cousin, but documentation debt is about absence of artifacts. Intent debt can exist even when documentation is present, if that documentation describes what the code does without explaining why the constraints exist. This distinction is subtle but critical. You can have zero documentation debt and catastrophic intent debt simultaneously. That is precisely the failure mode AI code generation creates. Finally, emerging AI governance frameworks, NIST ARMF of 2021, as model behavior, bias, and organizational accountability. They do not yet address the code comprehension layer. Intent debt fills a gap that even these frameworks have not formalized. Understanding this landscape tells you something important. Intent debt is a novel problem class, not a relabeled old one. And that novelty is exactly why the tooling designed to solve it looks unlike anything that came before. Let me close this chapter with a look forward. Because the teams that are getting this right today are already building towards solutions that not yet fully exist, but are becoming visible on the horizon. The first emerging direction is AI-assisted intent recovery, using large language models not to generate new code, but to interrogate existing AI-generated code and reconstruct probable intent. Think of it as forensic archaeology applied to your codebase, asking the model to reason backward from implementation to rationale. Early experiments show this works surprisingly well on isolated functions, but degrades quickly at module boundaries where context is lost. The second direction is what I call prompt archaeology, systematic tooling to recover and version the original prompts used to generate AI code. If the prompt was the specification, then the prompt is the intent. Some teams are already building prompt registries alongside their code registries. This is nascent, but architecturally coherent. The third and most consequential direction is intent-aware code generation itself. LLM coding assistants explicitly designed to embed rationale in line as they generate, not as an afterthought, but as a first-class output. Imagine Copilot that treats a co-located decision record as mandatory output alongside every non-trivial function. This is not science fiction. It is a prompt engineering and fine-tuning problem that several teams are already working on. The future of this space is not humans documenting AI code. It is AI documenting its own reasoning, continuously, as a structural invariant of generation. We have now seen how leading teams applied all of this in the real world. In our final chapter, we will synthesize everything into a single action framework you can take back to your team on Monday, including the one decision you must make in the next 30 days before your intent debt compounds past the point of practical recovery. We've traveled through 5 chapters together, and now it's time to compress everything into a single, unified mental model you can carry with you into every architecture review, every sprint planning session, every AI-assisted coding decision you make from this point forward. Let me show you how all the pieces lock together. At the center sits the core crisis, AI-generated code that no one truly understands. From that crisis, 3 distinct debt types radiate outward. Technical debt, the one we've known for decades. Cognitive debt, the invisible tax on human comprehension. And intent debt, the newest and most dangerous, where the AI behind every decision is silently erased. Each debt type feeds the next in a cascading failure loop. Top of that foundation, we layered the 3-tier taxonomy, the prompt layer, the decision layer, and the evolution layer, each requiring its own preservation strategy. The severity matrix then gave us triage logic, how to rank which gaps in intent are critical versus merely inconvenient. And finally, the 4 preservation principles, prompt as artifact, constraint-first prompting, rationale review gate, and the living intent map, form the antidote. These are not isolated tools. They are one integrated system. Here is the question that determines whether you've truly internalized this framework. Can you draw this map from memory on a whiteboard in your next team meeting? A framework is only as powerful as the vocabulary you use to wield it. Before you walk out of this lecture and into your next engineering discussion, let's run a fast vocabulary audit, a checklist of every core term from this lecture that you should now be able to define confidently, use correctly in conversation, and teach to someone else. That last criterion, can you teach it, is the true test of comprehension, not just recognition. Intent debt, the accumulated loss of decision context caused by AI-generated code that lacks rationale documentation. Cognitive debt, the growing gap between what the codebase does and what any human on the team actually understands. Technical debt, the classical concept of deferred quality, still relevant, but no longer sufficient on its own. Prompt as artifact, the principle that the prompt used to generate code is a first-class engineering document, version controlled alongside the code itself. Constraint-first prompting, a discipline of leading every AI prompt with explicit business rules, regulatory constraints, and non-functional requirements before stating the task. Rationale review gate, a mandatory checkpoint in your PR or code review process where the BWI must be documented before a merge is approved. Living intent map, a continuously updated architectural document that captures the intent layer of your codebase, not what the system does, but why it was built that way. If any of these terms felt even slightly unfamiliar just now, that's your signal to revisit the specific chapter where it was introduced. In the next section, you'll get the exact actions that turn these definitions into muscle memory. Insight without action is just entertainment. So let's make this concrete. Here is your 30-day implementation roadmap. Not aspirational, not vague, but specific enough that you can open your calendar right now and block the time. Week 1 is about diagnosis. Run a comprehension survey with your team. Ask every engineer to rate their confidence in explaining any arbitrary module they did not personally write on a scale of 1 to 5. Then run a bus factor audit. Identify the 3 modules where only one person can explain the intent. Those modules are your highest risk assets. Have the conversation. What happens if that person leaves tomorrow? Week 2 is about changing behavior at the point of generation. Mandate constraint-first prompting for all AI-assisted coding tasks. Establish a prompt artifact policy, even a simple shared folder in your repository where prompts are stored alongside the code they generated. This costs almost nothing and pays dividends immediately. Weeks 3 and 4 are about structural change. Take your highest risk module, the one with the worst bus factor score, and build its first living intent map. This is your proof of concept. One map, one module, done properly, will demonstrate the value of the entire framework to your organization more powerfully than any presentation you could give. The teams we studied in the previous chapter all started exactly this way. One small, visible win that created organizational permission for larger transformation. Your 30-day goal is not to solve intent debt. It is to prove that solving it is possible. You've now completed the core framework. But no single lecture exists in isolation. Every concept is a node in a larger knowledge graph, and knowing where to grow next is itself a strategic skill. Let me point you toward 3 adjacent domains that will amplify everything you've learned here. First, AI engineering governance. As organizations formalize their AI-assisted development practices, governance frameworks are emerging. From ISO 42001 for AI management systems to NIST's AI risk management framework. Intent debt is a specific manifestation of a broader AI governance problem. How do you maintain accountability and auditability when the generative tool is a black box? Study this space. Second, documentation as code systems. Tools like Backstage, Architectural Decision Records, ADRs, and Docs as code pipelines using Markdown and Git are the infrastructure layer that makes living intent maps scalable across large organizations. If you want to operationalize the principles from this lecture, this is the toolchain to master. Third, cognitive load theory in software design. John Sweller's original research on cognitive load and its application to software complexity by researchers like Linda Rising and Michael Feathers gives you the scientific foundation for why cognitive debt is not just a metaphor. It is a measurable neurological phenomenon with direct implications for team productivity and system reliability. These 3 domains are your next chapters. The question that should stay with you is this. In the AI-assisted future we are all building together, who is responsible for preserving the intent? The engineer, the tool, or the organization? The answer, as you now know, is all 3. And it starts with you next Monday morning.